Studies the rates at which a chemical process occurs, that is the kinetics. So beside information about the speed at which the reaction occurs, kinetics also shed light on the reaction mechanism. So apart from the chemical kinetics actually is also giving us information on the reaction mechanisms apart from measuring the speeds at which the reaction take place. So it also gives us an idea on how the reaction itself take place. So when we said reaction mechanisms, it means it's a step-by-step process in which a reaction take place. So that is what we mean in the chemical kinetics. So it means that chemical kinetics is providing us with two information: the speed at which the reaction takes place, also the mechanisms of the reaction. So now, these are the outlines that we are going to look specifically. What we did previously is just an introduction. So this reaction rate, we are going to look at this as what we are going to look at. Number one, reaction rate. That is how we measure the reaction. How are we going to measure the reaction? That is the reaction rate. Then the next one is rate loss. When you said rate loss, it means that is how the rate depend on the amount of the reactant. Assuming if you have 2 or 3 reactants, so is it that the reaction depend on the amount of all the reactant, or it depend on 1 or 2? And if it depend and if the reaction depend on all, but which one the reaction depend more on? Then the next thing also we are going to look at the integrated rate loss. That is how to calculate the amount left or time to reach a given amount. Then also we are going to look at half-life. Half-life, it means how long it takes to react 50% of the reactant. That is, if you have a reaction, so half-life will give us an idea on the time in which the 50% of the reactant are converted to products. And then the next one is Arrhenius equation. So under Arrhenius equation, we are also going to look at how rate constant changes with temperature. And then the mechanisms, that is the links between the rates and the molecular scale process. That is how the reactions are, or how the reactions is really taking place. That is the step-by-step process in which the reaction is taking place. Okay, so now we are starting with the reaction rates. So now, reaction rates. Rates of the reaction can be determined by monitoring the change in concentration of either reactant or product as a function of time. So now, look at it. This is the reaction at time 0 and at time 20 seconds and also at time 40 seconds. So you see the reactant here is A and the product is B. So now look at this. We have 1.0 mole of A and 0 mole of B at times 0 second. But at 20 seconds, it means that the reactant, which is the rate A, is now converting, or is now start converting to produce B. So meaning that here, the number of molecules of A are decreasing. Look at it from here. We have 1.0 mole of A at time 0, but at time 20 seconds, we have 0.54 mole of A, meaning that it decreased by 0.46 mole. And at the same time, look at it. At times 0 second, we have 0 mole of B. But at 20 second, we have 0.46 mole of B. So also at 40 second, we have 0.30 mole of A and we have 0.70 mole of B. So it means that with time, more of A are converting to produce B, and more of B are producing at the same time while A are decreasing. So meaning that in this reaction, you can monitor the rate of this reaction by determining the change in concentration of either the reactant, which is A, or the products as a function of time, meaning that with time. So notation for stoichiometry. If you see these square brackets in chemistry, it means that this square bracket here means concentration. So it means that here we have concentration of reactant A, and we have B here means the concentration of the reactant B. Okay, so this is what we mean by the rates of the reaction. So the next thing now is for the reaction. If we have A to produce B, so there are two ways of measuring this rate of the reaction. Number one, the speed at which the reactant disappears. Of course, from the previous slide, I said that usually the concentration of A are decreasing while the concentration of B is increasing. So if we want to measure the rate of the reaction, we can measure the disappearance of the reactant, which is A, or the speeds can be measured at which the product can be appear. So you see that as A is disappearing, so B is appearing. So reversible reactions, as a product accumulate, in a reversible reaction, as a product accumulate, they can begin to turn back into reactant. So in the case where we have a reversible reaction, reversible reactions is a reaction in which the reactant can be converted to product, and the product at the same time can be converted to produce the product. Sorry, to be converted back to produce the reactant. So early on, the rates will depend on only the amount of the reactant present. So we want to measure the reactant as soon as they mixed. So if we have A and B, maybe as our reactant, so we can start measuring the rate of the reaction as soon as those reactant mixed. So a general way of measuring the rate of the reaction is in terms of change in the concentration per unit time. That is the change in the concentration of the reactant or product with time. In the case of the reactant, the concentration of the reactant are decreasing with time, and the concentration of the product are increasing with time. That is how we measure the rate of the reaction. So now look at it. At the instantaneous rates, the change in the concentration of A with time limits to delta E over delta T. So most common units of rate is molar per second. Molar is the SI unit of concentration, and time is second. So rate can be measured with molar second. So reaction rates is the change in the concentration of a reactant or product with time. This one is clearly stated. So now look at it. The rates, if you want to measure the rate, you can measure the rates in the disappearance of A with time. So because it is decreased, usually in the reaction, the concentration of A is decreasing with time. That is why we have this negative. While if it is in the case of increase in the concentration of the product with time, so it is positive. So delta A, that is a change in concentration of A over a period of time. That is what this means. And look at it for the product. If you want to measure the appearance of the product, so it's the change in the product with time. So, and it's positive because it is increasing while A is decreasing. That is why it is negative. So because the concentration of A decreases with time, So that is why concentration of A is, the change in concentration of A is negative. So look at it. So reaction rate and stoichiometry. To generalize for the reaction, the rates can be measured at -1 all over A times change in the concentration of A with time, or -1 all over B times with the change in concentration with T, then 1 all over C times change in the concentration. So you see the change in concentration of C and D are all in the reactant, while A and B here are all the products. So you see the reactant decreases, while here are products and they increase. So you see, it's this equation we use to make this expression. 1 over A, because A here, small letter a is in mole of A, of capital A, and B is the small of capital B, and continues like this.